Still attending the machine learning track. I'm pleased to announce the next talk, which will be on Hyperopt, a Python library for optimizing the hyperparameters of machine learning algorithms. And this will be given by James Bergstra from the University of Waterloo.
Thank you. Yeah, so I guess the title's already been read. My name is James Bergstra. I'm a postdoc, so still in academia. This is joint work with Dan Yamins and David Cox that I did last year. So what is context and motivation for this work? So we just saw the general introduction to the machine learning, and didn't go into a whole lot of details about what hyperparameters are, but did mention a few things about, like, you know, if you're trying to fit an SVM, then you have to adjust the margin parameter. If you're doing a decision tree, you got to adjust the number of leaves and the splitting criterion and so on. So you know, a lot of the most tedious aspect of doing machine learning is actually tuning all these fiddly little parameters that adjust how exactly a machine learning algorithm actually works. So that's the kind of traditional view of hyperparameters. But I actually want to kind of draw even a bigger circle around the domain I'm trying to study here, which is to say that like, even the choice of algorithm itself is kind of a hyperparameter. Like, a lot of the time when you start with data, you know, you don't really care whether you get good predictions out of a support vector machine or a decision tree or a naive Bayes model. All you care about is that you get the right answer when you put in the data. So even the search over possible algorithms is kind of like a nuisance parameter that can be treated pretty much the same way as the hyperparameters. And to draw the circle even bigger, you know, you can even roll in a lot of the pre-processing arguments into that very same story. So, like, should you do that PCA and project down to 2 dimensions, or should you do the PCA and do it down to 3 dimensions or 5? And should you normalize it like he was doing for the figure, or should you not normalize it? Like, really, who cares? Just try them all and see what works and go with that. And unfortunately, trying them all is impossible because there's just like an innumerable number of possible ways of putting together all these different algorithm components. So it's really a kind of a daunting configuration task to search through that whole space. And that's what I think of as hyperparameter optimization. So usually what people do is, you know, you think about the problem and you use your intuition, or you read some papers and you go with what's worked in the past. You configure things manually and you do a bit of a grid search at the end to try and kind of refine what you thought were the most important hyperparameters that you were optimizing. And I did some research that showed that people are actually not very good at this. The grid search you do at the end is inefficient. The manual search you do at the beginning gets you to the wrong kind of local optimum. And I actually showed in some research about tuning neural networks that even random search in neural network space can find the best models for several data sets way faster than people. So that was what was motivating this work on hyperparameter optimization. Yeah, I'm trying to use the IPython slideshow too. It doesn't look quite as slick as when Fernando does it. But yeah, so why would you want to use algorithm configuration to configure, or why would you want to use algorithms to configure your other machine learning algorithms? Number one reason, you want to find what works. Number two reason, you want to do reproducible research. So all that fiddling at the command line and using your intuition is tough to communicate to other people, and is what makes machine learning results hard to reproduce. So if you can just run an algorithm from the beginning that searches through things for you, even if it's a stochastic one that doesn't exactly do the same thing multiple times, you can still hand that off to somebody else and get them to reproduce pretty much what you got. You want to empower your users. So I was talking about this in neural networks a bit. One of the reasons that neural networks are not in scikits right now is because there's too many hyperparameters and it's too much of a pain to even use those algorithms. So there's been kind of a barrier to getting them into that sort of standard library where they're trying to provide easy tools. I think with hyperparameter optimization as being part of the story, you can make a neural network an easy thing to use. So in order to, like, you know, make hard algorithms easy to use, hyperparameter optimization is like the way to go. And fuzz testing for free. If you know what fuzz testing is, it's the use of random inputs to try and test all the corner cases of combinations of inputs to your code to make sure you got everything covered. If you just do things by hand, you know, you don't really explore the whole space. But when you search automatically, it gets all your bugs. So you're going to get really solid code by the time hyperparameter optimization works. Overview of the talk. I'm just going to describe this library. I'm not going to describe too much the research that motivated it. I'm going to talk about how you encode domain knowledge about what kind of machine learning works into what's called a search space. And I'm going to talk about how to define an objective function to assign value to points in that search space so that you can use an optimization algorithm to find the point in the search space that has the best value. And then I'm going to talk a little bit about some other kind of nice stuff you can do by using the trials object to analyze the results of search. Hyperopt is actually a parallel searching kind of framework thing. So it doesn't use IPython yet, but it does allow you to use MongoDB to do lots of searching in parallel. So this is a tool you can use to search on a cluster. I'm not going to talk too much about how you do that. I'm just going to sort of show you that it's easy. I'm not going to talk about how that works. And then ongoing work. So just to launch straight into some code here, this is kind of the structure of a program that uses Hyperopt. Can you all see it? Is it big enough? Zoom in. That's better, I guess, right? Yeah. All right, so yeah, Hyperopt. You can import it. It's a Python module. The first thing that you do to use Hyperopt is to define a search space. So what are you going to optimize over? And in contrast to like SciPy's optimization routines where you put just an open range or you put some bounds or something like that, the way you're going to specify a search space in Hyperopt is to imagine that you're doing random search and you're going to design a structured probability distribution that can sample from all the different kinds of configurations that you'd like to try. So, I mean, that's where I started with this work. I was doing random search. This is the form that you use to outline what is the domain of interest. So we're not doing machine learning yet here, but just to give you a flavor of what's going on, this search space consists of pairs. So we're, this is a list of length 2, and the first element of our list is going to be a number between 0 and 1, and the second element of our list is going to be a number from a normal distribution. It could be anything. So we're going to be searching over pairs of numbers here. You can see that I've named these hyperparameters x and y. That helps Hyperopt, but it doesn't actually change the space. But you do have to give names for hyperparameters. So if you describe this search space as a probability density, then the next thing to do is to say how you're going to score points in that space. So that's what this function f here is doing. So f is going to just square its 2 arguments. It's not a very interesting function, but it gets the job done. This function just returns a floating point number. That's the function you're trying to optimize. And then you call fmin. So that's kind of a familiar pattern. You call fmin, say I want to minimize this function over this space using this algorithm, and I'm going to give it this many chances. So if you call this function, it will go off, call your function at 100 different random points drawn from these distributions, and picks the best one. So random search here happens to score the actual minimum of this function 0, 0. Random search gets kind of close. You can also use different algorithms. So the point of this library is to make the algorithm something you can swap in and out. So you can call use this other algorithm instead, and it gets a bit closer to the minimum. So this is kind of the flavor of the kind of thing you're going to do if you're going to use Hyperopt to optimize hyperparameters. But in machine learning, you're going to replace this function f with something that involves doing some machine learning. On the next slide, I think I've got a bit more here about how you can define search spaces. So that first search space just had like 2 simple variables. We're searching over a vector space that you could have done with SciPy. One of the advantages of using Hyperopt is that you can search over a bigger range of different kinds of spaces. So you can search over log uniform and log normal variables instead of uniform and normal. So those would be variables that can go down to a certain point, but they can't go past that. So that's like a one-sided bound. If you're using log scale, that means that when you're doing random search, you're more likely to pick points that are close to that bound and less likely to pick points that are really huge. So if you're trying to optimize the C parameter of an SVM, that's probably a good choice to use. You want to choose something like, usually it could be around 1, it could maybe get close to 0, or it could be up as big as 1,000. So that's a good example of a log normal variable. Quantized distributions are good distributions for describing, shoot. Quantized distributions are good for describing numbers of things. So if these Q uniform and Q normal are for describing counts. So if you want to describe like a number of examples at a leaf of a decision tree, and you're not really not sure what it is, just say it's a quantized uniform between 0 and 10 or something, and then that'll be like describing that kind of search space. You can also have quantized log normal things. A categorical variable is one that doesn't have any kind of order to it. So if you want to optimize over random seeds, make that a randint. That means it's just different integers, and there's no kind of similarity between integers that happen to be close together. And the most interesting kind of parameter, which I'll show on the next slide here, is called a choice. And the choice is, well, I'll just come back to it on the next slide. You can also put other expressions in the search space too. So you don't just have to describe the numbers themselves in a list. You can describe a whole kind of functional program. And I think the best way to illustrate that with operators and containers and stuff is on the next slide here. So this is a sketch, it doesn't work yet, of how you would use something like Hyperopt to optimize something like scikit-learn. So what you could do to do that is you can add the primitives of scikit-learn to the kind of domain of search of Hyperopt, and then you can write down here like a stochastic program that generates scikit-learn objects. So what's going on here is that I want to say that my machine learning algorithm is going to involve some pre-processing, but I don't really know what it is. So for my search, I'm just going to make it a choice. Either I'm going to have PCA, or I'm going to have a Gaussian mixture model to be my pre-processing. And the number of components is going to be a Q log normal, you know, with a certain range. That means like probably is going to be a PCA with around 10 components. That could be 3 or it could be 30. Either I'm going to whiten it or not. You know, these are the hyperparameters that come from the documentation of scikit-learn. For the Gaussian mixture model, I'm going to go for another number of components that's in some range. The covariance type could be either spherical or tied or diagonal. So if you read through the documentation of scikit-learn, you see there's all these choices for every single kind of machine learning component or pre-processing or classifier. And what this Hyperopt language allows you to do is to describe a whole kind of search process and your domain expertise for like how many PCA components usually make sense, how many Gaussian mixture components usually make sense. And then like for the classifier, you can do the same thing to describe the arguments to the decision tree and support vector machine. So you can lay out this whole search space, and then you can ask Hyperopt to sample over that, and it will search through all the combinations of pre-processing, classification algorithm, and so on. And you can actually optimize over that whole sort of structural space. So this code here is finally doing this sample. Sampling here from a hyperparameter space gives you these guys down here. So a sample from the space is this giant mess, which doesn't really fit on the screen anymore. But in particular, I'm sampling from a dictionary here that's got pre-processing and classifier. The classifier is a decision tree classifier in this case, which happens to have certain kind of parameters chosen automatically. So I've used this approach in my own research to search through pretty huge search spaces. I was doing computer vision, and this is kind of a figure that explains the different possibilities for putting together a multi-layer convolutional neural network for image labeling. And so instead of choosing between a decision tree and a support vector machine, we're making a whole lot of choices along the way between like how many layers to use, how to normalize various filters, and so on. So this search space actually had 238 hyperparameters in it that you could never really search through by hand. And it's a huge search space, but actually the Hyperopt algorithm was the TPE algorithm in the Hyperopt library was able to actually search through that whole space and find what is currently the best known points for this modeling approach. So the algorithm works to some degree. Just to give you a little bit of a sketch of how the optimization works. in a more realistic setting, I'm going to come back from machine learning a sentence, because machine learning algorithms are like, there'd be more than one page worth of code to show. But I want to show like how it would work in a case where you've actually got some choices here. So this is another kind of code sample that shows a search space and a more realistic objective function. And it also shows how to use a trials object to actually find out about like what happened during search. Because usually if you invest in so many hours of computation, you don't just want to know like one single floating point number at the end of the day. You want to have a whole history of all kinds of stuff that you computed along the way. So Hyperopt lets you do that. So this space in particular, just a toy space here, we only have one choice, and we're going to choose between two kinds of dictionaries. There's a type 1 dictionary and a type 2 dictionary. Like whatever. It's just an example. And we're going to have a random integer r. It can go between 0 and 9. And the objective function is going to get samples from that space, which is going to be a dictionary, a string, and a number. And it's going to compute a loss that depends on those Python objects that it unpacks. And then it's going to return a dictionary instead of a score. So returning a dictionary instead of a number is how you can like keep track of extra stuff that you computed during your experiments. So in this case, we're going to return a status. That's a Hyperopt thing. The loss is the number that you actually want Hyperopt to optimize. So you always have to return a loss. And then as well as the loss and the status, you can fill that dictionary with all kinds of other stuff that you like. So in this case, I'm just going to put another list in there that has some kind of computed value that's going to stand for something I want to associate with the result of this trial. So when I call fmin on this guy, I can pass this trials object, use the same random search as before, but by passing the trials object means that for each one of these 10 function calls, they get kind of stored up in the trials object, and I can look at it later. So the trials object gets populated by the call to fmin. And that's how we're going to be able to analyze the result of our search. So for every trial here, I'm just going to print it out. And that's going to give all this stuff here. All kinds of dictionaries with domain attachments and work directories, and all this kind of bookkeeping stuff that's inside of the trials object. But what's worth noting is the result here and the values over here. So those two guys in this dictionary, if you want to use the library, you can poke through the whole dictionary and find out all kinds of stuff that's in there. But the result and the values is going to help us do some analysis later. So we can make plots, from this particular search. We can use the trials and say, for example, plot what was the relationship between time and the case random variable that we were using before. So if you want to look back here for a second, case was the name of the choice hyperparameter that it was going to choose between one kind of dictionary and the other kind of dictionary. So we can see that cases over time is either 0 or 1, because it was either the one choice or the other. This is an integer. Since we're doing random search, it just kind of goes back and forth between the two of them. If we want to look at something a bit more interesting, we can look at the relationship between the loss. So here we got the actual loss value that the function that the Hyperopt is trying to optimize, and the value of r. Why not? So to go back and look, the loss function that we returned in our objective was r plus something. So then when we look at the plot, we see a linear relationship between r on the bottom axis and the objective of the function, which is going up and down. Point being, you can use the trials object to go back and understand relationships between your variables that were discovered in the process of search. So So that will give you some insight into your function space. So if you're searching over machine learning algorithms, you might want to plot loss against the kind of algorithm you're using. You might see after the fact that all the jobs that were using support vector machines did great, and all the jobs that were using naive Bayes did terrible. And then you'd be able to learn something about how to do machine learning on that data set. Parallel search is something which I mentioned earlier. It's easy to do it by just replacing the trials object with a different kind of object that's aware of a database. So I was using MongoDB. I think I'd like to use IPython's parallel infrastructure in the future, but right now that's not implemented. Instead, you have to load up a MongoDB instance in the background, and then you have a lot of workers, and the fmin call actually just sends jobs to MongoDB. The workers pick up the jobs, do the jobs, put the results back in MongoDB, and then the fmin is polling MongoDB, sees the jobs have been done, and search proceeds kind of asynchronously like that. So you can stop fmin after a couple days of search and turn it back on later, and it will just keep going where it left off because it's using state that's in the database. Right, so using Mongo trials is as easy as just using a different constructor and passing it to fmin like that. The roadmap for Hyperopt in the short term is to get some more algorithms into it. So there's there are people working towards a workshop at NIPS this year, I think. If you go to that conference, you might see some progress on different algorithms being rolled into Hyperopt. And application packages for actually using this library to encode domain knowledge about specific things. So I've encoded my knowledge about how to do convolutional networks, but that doesn't exist yet for searching through the different classifiers and so on that are in scikit-learn. So that's kind of an ongoing project. Yeah, tighter IPython integration too. So in summary, Hyperopt and algorithms in general are at least as good as people at configuring the hyperparameters of machine learning algorithms, and Hyperopt helps you use that in your own work. The library provides a language for describing what parameters make sense, sort of encoding your domain expertise about what represents reasonable ways to put these things together. Algorithms for searching configuration spaces, so that's the TPE algorithm I mentioned. Data structures for doing the analysis after the fact, and some parallel infrastructure for taking advantage of a cluster for doing search. So far, Hyperopt is undefeated against domain experts in neural networks and computer vision, with some caveats. Right, so scikit-learn version of this is sort of in progress. So that's all that I have. Thank you for listening. Okay. Could you?
In your application where your hyperparameter space has 238 dimensions, how many trials would you have to use to get a sense that you covered this space?
So the question is, in the hyperparameter search problem with 238 dimensions, how many jobs did it take to cover the space? I have no idea how many jobs it would take to cover a 238 dimensional space. It's sort of weird to think of this as an optimization problem in the normal sense, because there's no hope that this possibly optimized every one of those 238 dimensions. I used on the order of like 1,000 trials. So almost about on the order of number of dimensions themselves. And so I just want to kind of emphasize that the purpose of Hyperopt is not always to completely optimize the space. It's simply to do better than people. And people are terrible at that. So it's sort of an easy benchmark to beat.
You set the bar pretty low.
That's standard practice.
I have a question.
Next question. Yeah.
And so this hyperparameter optimization is, I would argue, in fact, a learning algorithm. So really what you want to do if you're searching over so many parameters on many nonlinear algorithms, you want to have a good estimate of what your out-of-sample error is. So how do you integrate in with like cross-validation and do subsetting?
All right, so the question is, how do you use Hyperopt in a valid kind of model evaluation protocol? So I've been using what's called cross-validation for the most part, which is to say what Hyperopt actually optimizes is validation set error. So you take your data set and you divide it into 3 pieces. You've got your training data for actually training the classifiers on the inner loop. validation data for selecting between the classifiers. So you search through the whole set of classifiers as much as you got patience for the best validation score. And then once you got a model that's the best on validation, you got your model, and then you run it on the test data to see like how much you overfit. And for different kinds of models with different amounts of data, you can see more or less overfitting. That's a protocol. Yeah.
So random search seems kind of inefficient, just naively. I was just wondering what the kind of state of the art is for intelligent optimization algorithms. I mean, you mentioned this TPE. Can you talk about what's behind that?
Yeah, exactly. I didn't have any time to go into the algorithms themselves. The question is, random search seems really bad. What is the better algorithms for doing a search? The answer is that random search is actually surprisingly good. That's part of the answer. The reason is that of all the 238 hyperparameters, there aren't that many that make a big difference to performance. And you don't necessarily know ahead of time which ones of the parameters those are going to be. But by doing random search, you actually end up efficiently searching every possible subspace. So random search is only as bad as random search on the very few dimensions that matter. So if there's only a few dimensions that matter, random search is pretty good. The TPE algorithm is like taking random search and then slowly refining it to not choose values for hyperparameters that are strongly correlated with terrible performance. So it's sort of the next least dumb thing. And I think that's so far competitive with the state of the art. There are methods for very efficient search in low dimensions, but high dimensional weird search spaces like the ones for hyperparameters is like, it's just a hard search problem.
We'll take one last question and then we can move to the break and talk at will. Yes, please.
All right, last question.
So how do you handle search spaces that are not necessarily, well, let's say donut shaped, places where exclusion between parameters, can you handle those?
Right, so the question is, how do you accommodate holes or like infeasible regions within the search space? So you can easily describe a search space over like several so-called independent variables, when in fact your program doesn't work for some combinations of those in the middle, right? So that's a good question. Hyperopt deals with it in one way, which is kind of insufficient, which is kind of that your job can just return an error, and then the algorithms can pick up on the fact that there's a ridge of terrible performance in the middle. But to actually communicate those kinds of holes, you'd have to probably reparameterize the way you describe the search space to not have a hole in it. Yeah.
Thank you again, James. And